Why does the siren sound change as it passes by? The Doppler effect story. You've probably experienced this at least once. A speeding ambulance approaches with a loud nee-naw, nee-naw. As it gets closer, the sound rises in pitch, and as it passes by, the pitch suddenly drops. Is something wrong with the siren? Why does it sound so different? This strange phenomenon has fascinated scientists for centuries, and today we know it as the Doppler effect. The idea was first proposed in 1842 by Austrian physicist Christian Doppler, and then it was in 1845 that Dutch scientist Buys Ballot set out to prove it with a brilliant experiment. He loaded trumpet players onto an open-top train, and as the train sped past a group of listeners, they carefully observed how the pitch of the sound changed. And guess what? As the train approached, the sound was higher pitched, and as it moved away, the sound became lower. A common misunderstanding. Many people believe the Doppler effect is about sound getting louder or quieter. That's not quite right. The Doppler effect is not about amplitude, but about frequency. Imagine playing a musical scale, do, re, mi, fa, sol, la, ti, do. The pitch changes, not the volume. Volume depends on distance, not the motion of the sound source. So don't confuse Doppler shift with simply hearing something louder or softer. Light experiences Doppler shift too. Surprisingly, this effect doesn't only apply to sound, it also works with light. When a light source moves toward you, its frequency shifts toward blue. When it moves away, it shifts toward red. This principle is what helps astronomers determine whether stars or galaxies are moving toward us or away from us, a key to understanding the expansion of the universe. And again, it's the color that changes, not the brightness. Brightness follows a square law with distance and has nothing to do with the Doppler effect. How can we visualize the Doppler effect? Imagine someone standing still and shouting, beep, beep, beep. The sound waves ripple outward in perfect circles, equally spaced. Now imagine the person starts running forward. In front of them, the sound waves bunch up, shorter wavelengths, higher pitch. Behind them, the waves stretch out, longer wavelengths, lower pitch. That's why we hear a rise in pitch as something approaches, and a drop in pitch as it moves away. Where is the Doppler effect used today? Police speed radar. It measures how fast cars are moving, based on frequency changes. Astronomy. We observe red or blue shifts in starlight to track the movement of celestial bodies. Medical ultrasound. Doppler ultrasound measures blood flow and heartbeats using this very principle. Next time you hear an ambulance pass by and the siren sounds weird, don't just brush it off. That's your ears catching a glimpse of the laws of physics in action, because even in everyday sounds, there's a quiet echo of the universe and the science that helps us understand it. The Doppler effect may be invisible, but once you hear it, you'll never listen to the world the same way again.